Our third video for this unit is about the conservation of momentum. Our objectives for this video is at the end, you should be able to say, confidently, I can state the law of conservation of momentum, describe how the law of conservation of momentum applies to collisions, and explain the difference between elastic and inelastic collisions, the two different types. Before we move on to the fun part of collisions, first we should visit the law of conservation of momentum. Now when you see that word conservation, you might think of wildlife, and how there are conservationists that are trying to keep certain areas of wildlife the same. Well, in physics and chemistry, conservation kind of means keeping something the same, but I want you to think about it as something that cannot be created or destroyed. So, if we replace this definition into the law of conservation of momentum, you can come up with a definition that momentum cannot be created or destroyed. In other words, it stays the same. Now here's a more formal definition below. The law of conservation of momentum states that the momentum of an object or system remains unchanged unless acted on by an external force. Now there's a new word in here, and that word is system. We'll talk about what a system is in just a second. First, let's consider momentum in objects. So the momentum of an object is going to remain unchanged unless acted on by an external force. Let's look at this picture right here. What objects do you see? Well, there are two, the bowling ball and the bowling pin. Now you can imagine if they're just sitting there, and you think about our old formula, momentum equals mass times velocity. If both of those objects are at rest, their momentum is going to be zero. How do you change the momentum of a bowling ball? You put an external force on it. For example, your arm applying a force to the bowling ball. And how can the momentum of the bowling pin change? Well, when the ball strikes it, it's going to transfer some of its momentum to the bowling pin. But the momentum of both would have stayed zero unless an outside force acted on it. Similarly, once they're set in motion, the momentum is going to stay the same unless another force acts on it, like the back of the bowling alley, or friction. Now you can look at the bowling ball and the bowling pin as a system too. So, what's a system? It's going to be two or more objects isolated from external forces. A lot of times in physics, a dashed line will be drawn to define a system. So what makes up this system? Let's draw a dashed line around it. And the system in this case is going to be the bowling ball and the bowling pin together. Now that we've defined a system, let's look at how momentum is conserved in a system. So the law of conservation of momentum told us that the momentum of a system remains unchanged unless acted on by an external force. Now this is a complex concept, and it's one that requires us to remember all of our Newton's laws of motion. In this system, when the bowling ball strikes the bowling pin, that's going to be the action. The reaction is going to be the bowling pin striking the bowling ball in the system. And the action force and the reaction force are going to be equal and opposite. So what happens is when the bowling ball and the bowling pin collide, the bowling ball is going to lose momentum, and the bowling pin is going to increase momentum. But the amount of loss of momentum by the bowling ball is going to be equal and opposite to the amount of momentum gained by the bowling pin. Now remember, the force is going to be equal, according to Newton's third law of action and reaction. But the acceleration is going to depend on the mass, so it's going to be unequal. And since the bowling ball has a much larger mass than the bowling pin, its change in acceleration is going to be less. And that has to do with Newton's second law, which we wrote like this. So let's recap a little bit what just happened with that bowling ball, bowling pin system. We said that the law of conservation of momentum said that the momentum of a system will remain unchanged unless acted on by an external force. So another way of saying or thinking about that is to think about when two objects collide to make up a system. The initial total momentum, the momentum of both objects together, is going to equal the final total momentum. The total change in momentum is going to be 0, because in that example that we just used, the decrease in momentum of the bowling ball was equal to the increased momentum of the bowling pin, and that meant a 0 change in momentum. Now in a system, momentum can be transferred from one object to another, but the changes in momentum are going to cancel each other out, because they're equal and opposite. So all of these statements are just different ways to talk about the law of conservation of momentum. Now all of what we're studying this unit is to lead up to collisions. So I want to tell you a little bit about two types of collisions that we're going to be dealing with. One is called elastic, and one is called inelastic. Elastic collisions are also known as kind of like bouncy collisions, and that's where the colliding objects bounce off of each other perfectly. So what would happen, a really good example, is an example of pool, where one ball hits another and just bounces right off. An inelastic collision is when two objects stick together. So I think the best way to see the difference between the two is just to look at some examples. Here are some examples that I want to see if they're elastic or inelastic collisions. A classic example is pool balls. So here's a cue ball, and it's going to be hit by the cue. It would hit the 8 ball, and they'd bounce off each other. So this one would be elastic. Now here's a really cool picture that I found of, it looks like a defensive back hitting a receiver, and it almost looks like it's moving. Now whether a collision would be elastic or inelastic depends on how the defensive back tackled. I want you to imagine that he'd wrapped his arms around the player with the ball, and then they kind of fell to the ground as one, and that would be an inelastic collision. Now if the defensive player here didn't use his arms and they kind of bounced off of each other, then that would be more elastic. Now here's another classic example of a fish eating a smaller fish. So this fish would swim into the mouth of the bigger fish, and then they'd continue on as one kind of big fish almost. In other words, they'd stick together, and that would be an inelastic collision. So let's bring those two concepts together. Here we have 3 different systems. This system is made up of the object of the cue ball, object A, and the object of the 8 ball, object B. Together, they'd make up a system. We could call it system AB. Now what would happen is the momentum of each object would remain unchanged unless acted on by an external force. In this case, the external force would be the pool stick. Now once the pool stick acts on object A and changes its momentum, it could collide with ball B and change ball B's momentum. But after object A and object B collide, the decrease in momentum of object A is going to equal the increase in momentum of object B. They cancel each other out, and for this system, AB, momentum is conserved. This system is made up of 2 objects, the player in the green and the player in the yellow. When we do some more examples, what we're going to find is that when they collide, they become like one object, and both of their momentums change, but they're going to have one momentum together. We'll do more examples about that tomorrow. The same thing here. Remember, we have fish A and fish B, and together they make up this system, system AB. Now when these fish collide, both of them are going to change momentum, but the momentum is going to be conserved in the system. Now go ahead and do some practice problems on your problem set. Work with one of your clock partners, and if you're still feeling confused, ask for help, do the good practice problems in your book, or read your book and do the textbook Cornell notes.